So welcome all of you and thank you for joining us for the ASKAP Lightning Talks event. My name is Aditi. I'm from the Pawsey Supercomputing Center. I work in the marketing team and lead our digital engagement. And I'm here to kind of kick things off today. I would like to begin by paying my respects to the Whadjuk people of the Noongar Nation, whose land that we meet on today. And I would like to pay my respects to the elders past, present and emerging. I would also like to pay my respects to the elders and their lands on which you are today as well, as this is an online event. The ASKAP Lightning Talks are a series of short 5-minute presentations by Pawsey and ASKAP personnel as they overview the thing that gives them the greatest sense of anticipation for the coming year and beyond in astronomy. From a Pawsey perspective, we're expecting the arrival of our new systems, and we want to share our excitement today about them as well as their capabilities. So integrating that into ASKAP as well, hopefully you'll hear some really interesting stories and ideas for the future.
So first up, we have Matt.
Hello, everyone. Yeah, so look, it's a pleasure to kick this off. Should be an interesting afternoon. So I'm Matthew Whiting. I think I probably know most of you, I guess, but yeah, so I'm going to talk on ASKAP operations. I'll no, there we go. Yeah, so from the operations side with ASKAP, so we've got a very close working relationship with Pawsey. We have done since I think since there was a Pawsey, maybe even before, and it's important to us because the Pawsey systems are really, you know, an integral part of the telescope. So you can see this slightly old diagram to emphasize this fact. There's a couple of things that haven't quite come through, but never mind. Yeah, so this diagram's kind of indicating the amount of data that's flowing around ASKAP and where the important steps are in viewed from that side. The ASKAP's main feature of the phased array feeds. So these receivers allow it to form multiple beams on the sky, look in multiple directions at once, and rapidly cover a large area of the sky, enabling sort of the great survey science that we'll hear about shortly. This means a lot of data. So you can probably see we get sort of 2.5 gigabytes a second coming out of the correlator when ASKAP's observing. And that comes over the network down to Pawsey. And we have an ingest cluster there that is able to handle that data in real time, ingest it, write it all to disk so that it's ready to be processed. It's a lot of data. A typical 8-hour observation generates easily more than 30 terabytes of raw data. And data of this scale really requires high performance computing to process it, to produce the sort of data products that people are going to use for their science. To do that processing, was that me? If we to do that processing, we can go back. Sorry, that change just flummoxed me there. To do the processing, we use the Galaxy supercomputer at Pawsey. So that's shown here as the ASKAP central processor. That produces a whole lot of images and catalogs and spectra and so forth that go into the archive called CASDA that are served up to the community and used for science. Additionally, not strictly operations work, but through the grace of NCMAS and Pawsey partners, we do have an allocation on Magnus that further supports science team work by allowing further processing and analysis of the data beyond the operational stuff. So there are many ways where the Pawsey systems are critical for ASKAP to work. So my main interest is in the processing side on Galaxy, and so yeah, that next slide sort of illustrates the processing work that we do. We have a workflow that takes the raw data handles all the different processing tasks that are required and produces the data products that we need. The tasks come largely from the ASKAP-soft suite of packages, which has been custom written within CSIRO to make effective use of the high performance computing environment, deal with a lot of the specific needs of ASKAP data. So we have 36 beams coming from the telescope, and these beams are handled in largely independent data streams. A whole series of different tasks, some of which are quite computationally intensive. They can be distributed across many nodes of the cluster, and in fact, when this is running at full speed, we can fully utilize the resources on Galaxy. One of the things I think that we're most interested or most excited about for the coming year is really the advent of Photonics, the new system at Pawsey, and really the opportunity to sort of take our workflows and implement them on that and explore how we can best utilize the new architecture and the new technology to improve our processing performance even further. We have work to do to speed this up and get closer to sort of the goal of real-time processing. And I think Photonics and working with Pawsey is going to be crucial to that. So I'll leave that there and move on to actual science talks, and I look forward to talking with any or all of you during the discussion session. Thanks.
Okay, over to you, Andrew.
Thank you. I think I know pretty much everyone in the room. I'm Andrew Hopkins. I'm leading the EMU survey with ASKAP. Thank you very much, Anne, for accommodating me early in the program because I do have to leave at 1:30 for another meeting. So I thought I would just give a very quick overview of EMU. I think most of you know most of this, but there might be a few little snippets in here that some of you haven't seen before. So I'll just go through this quickly. And unfortunately, because I won't be able to stay around for conversation and questions afterwards, I will just encourage people to get in touch with me directly by email if there are things that you'd like to follow up. So in broad terms, EMU is the Continuum Hemisphere program with ASKAP. And I was rather amused a little while ago to realise that I'm doing my PhD thesis all over again, just on a slightly grander scale, because my PhD program was I think it was about a 3 or 4 square degree survey with the compact array to the same kind of sensitivity and resolution that EMU is going to be doing over the entire hemisphere. So I'm just taking my PhD thesis and scaling it up by a factor of 10,000 or so. As you have been able to read by now while I've been talking away here, we're aiming to get to sensitivities. Originally, the goal was to get to 10 microjanskis. We're moderating that expectation a little based on our experience with the ASKAP performance over the early science and pilot stages. We're hoping that we'll still be able to reach RMS noise levels of around 15 microjanskis over the full sky, with resolutions probably of the order of about 15 arcseconds over most of the sky. And depending on the sensitivity that we get to, detecting as many as 70 million radio sources, which is at least 2 orders of magnitude larger than the total number of radio sources ever measured to date. So that number may be not quite so large. If our noise level is a little brighter, then we might be detecting only as many as 30 or 40 million sources. So it's pretty important for us to push the instrument as hard as we can to make the best survey that we possibly can. The collaboration is very large and very international. We have around 400 members internationally, and we're continuing to add more pretty much daily. It's a very open collaboration. Anyone can ask to join. If you would like to contribute to the project, then feel free to send me an email. Really, the main requirement for joining EMU is a commitment to following the publication policy, which is kind of, in a sense, the glue that holds the team together, and which is aimed at trying to maximise collaboration across the very, very large team, and to give us the opportunity to identify and flag potential conflicts as people are doing research that might overlap with the projects that other people are interested in as well. We've had a very successful early phase of the project with the early science and pilot phase 1 data sets. There's a lot of science already coming out. I think I mentioned the number of papers there somewhere. Maybe I haven't. There's, oh yes, already over a dozen papers that we've published using early science and pilot data. There are, I think the number is probably now more than 50 approved projects that people are starting to work on with existing data. And people are also starting now to propose projects with the pilot phase 2 data. The other thing that EMU is putting a lot of work into is the EMUcat pipeline. This is designed to run more or less in real time as new EMU data comes in. The catalogues that get produced will be cross-matched with other catalogues. We're doing classification. We're trying to identify complex and extended sources, and produce a set of science-ready data products from adding information from catalogues such as infrared sky catalogues from WISE, optical catalogues, near-infrared catalogues, redshift data when they're available, and much more. Please feel free to have a look at the website. Send me an email if you would like to find out a little bit more, or if you'd like to be added to the team. Thank you very much.
Thank you, Andrew. So next up, we have George and the POSSUM project.
Okay, thanks a lot. Okay, yeah, so I'll briefly introduce POSSUM, and I'll just say that this is a project to study magnetism throughout the universe. On the next slide, there's a picture to motivate. Can I advance the slide? Okay, great. Yep. So one of the main things that we're trying to do with POSSUM is to understand the magnetic fields within. This is a nice recent picture of an edge-on spiral galaxy called NGC 5775 with magnetic fields reaching out of the galaxy actually into intergalactic space. Now, if you press next, you'll see that another graphic basically emphasizing that we can't see magnetic fields directly, but what we can see are the equivalent of iron filings showing us the location and direction of magnetic fields. And those iron filings, in our case, are cosmic rays, which emit radio emission and show us where the magnetic fields are. On the next slide, I show you that that radio observations, and in particular polarization observations with radio telescopes, are extremely powerful for finding these magnetic fields, both in emission, as I showed you on the previous page, but also in not quite emission, but also by looking at foreground effects on the polarization properties of background radio sources. This is encapsulated into an overall approach that we call rotation measure grid, which looks at the foreground effects of intervening objects. So if you push next, you'll see a picture in the top right, which is from a recently published paper by Craig Anderson, who I think is in the audience right now, looking at the impact of the fornax cluster, which is within the white circles in that figure, the impact of that cluster environment on background sources behind the fornax cluster. So in that diagram at the bottom, it's probably too small to read the detail, but the upshot of that diagram is that within the inner circle of the, or within the circles that are shown on the top right, there is an impact of the cluster environment on background polarized radio sources. And from that, we can derive information about the magnetic fields and ionized gas within the Fornax cluster. And that's the sort of bread and butter. That sort of analysis is the bread and butter of POSSUM. So on the next slide, you can see that this kind of work is a data processing challenge. We need to look at the data sliced up in all sorts of different ways, both in continuum spectral cubes with some image processing that's required along the way, and generating cubes in another space, which is called the Faraday domain, which gives us polarization information, all winding up in the petabyte sort of data domain. The pipeline diagram on the right is from Alec Thompson, who's also in the audience here, looking at polarization analysis of the ASKAP RACS survey, which has just been released. So I think the next page is my last one, I think, which is just about a few exciting science goals which we have in the short term. First, looking at the magnetic size of galaxies in the same sort of way as the Fornax cluster that I showed you a couple slides ago, and looking for magnetic structure in galaxy outskirts. Next, looking at the structure and magnetic content of the cosmic web, which is the large-scale structure that connects galaxies and clusters across the entire universe. And finally, within our own Milky Way, looking at the large-scale structure of the magnetic field and also the magnetic content of individual objects, such as supernova remnants, like supernova 1006, which is the one shown in the bottom right, which we are in the middle of looking at the magnetic structure with POSSUM data at the moment. Yep, so the next slide just has some contact info. So POSSUM is the polarization sky survey of the universe's magnetism. We also have, if you're interested in acronyms, as will come up later today, I think, there's two friends of POSSUM called Quokka and Qual, which you can ask me about if you like. Please visit our website and let me know if you have any questions. Thanks.
Thanks, George. All right, next we have up Tara. Now, Tara, would you like to turn on your camera and your microphone?
Yeah. Hi, everyone. So I'm Tara Murphy from the University of Sydney, and I lead the Variables and Slow Transients project. And so I think if we go to the next slide, okay, so the original science goals are vast. They're very broad. Apologies for the ASKAP people that have heard this before. But for others, the science goals range from things in our very local universe, such as flaring stars in our nearby galactic neighborhood, through to distant cosmological things, such as the afterglows from gamma ray bursts and supernova. And then in between, you have variability that's caused by things like scintillation as the signal travels through the interstellar medium. So the range of timescales that VAST is investigating is everything from the faster scales on which ASKAP images, seconds to minutes, through to months and years. And of course, in addition to all of the specific science goals, there's the untargeted survey context in which we hope to discover unknown classes of objects through their variable behavior. So if we go on to the next slide, thanks. So what we've done in the first pilot survey, which was 100 hours, is choose several regions of the sky along the equatorial strip, the region that coincides with the Emu and Possum observations, and then a region centered on the galactic center and the large and small Magellanic Clouds, to try out different aspects of this survey in terms of what science we can do and solving some of the technical problems. And so far, this has been very successful in the context of longer term variability. So we've discovered a whole bunch of new flaring stars. There's a lot, as well as being scientifically interesting in their own right. Flare stars are considered to be one of the most likely foreground confusing sources in the SKA era. This is the first survey I think we've done, the first transient survey, where we have actually started seeing that we're finding lots of stars in addition to everything else. And we've also done, for example, a successful search for GRB afterglows. And so there's we've explored all of those kind of longer timescale from hours to months timescales. In the next phase of the pilot survey, so if we could go to the next slide. Oh, sorry. I'll just do this slide first, and then I'll say what we're most excited about. So the other thing we can do is explore these deeper fields. So the VAST survey is like 12-minute observations of the footprint that I just showed you. But there are also many projects doing 10 to 12-hour observations of a single field. So this example here is one from the follow-up program we were running to follow up a LIGO gravitational wave event. And one of the exciting things about ASKAP there is that it can cover the whole LIGO error circle. This is the 90% contours in a single observation. And there are also, of course, the EMU fields and the POSSUM fields that are 10 to 12 hours on a single point. And then there are also targeted fields that were done as part of a project, for example, the Proxima Centauri monitoring campaign and the recent test observations that coincided with the test campaign. So with these 10 to 12-hour observations, we can then split them up and look for variability on shorter timescales. And that's something that one of my PhD students, Yuanming Wang, has been working on. So if we go to the next slide, what we see here is some of the results from Yuanming's work, where she found a series of intra-hour variables. And these in the middle there are two little videos of looking at these in the UV model subtracted images. So obviously doing the imaging of shorter timescales from these 10-hour observations is very computationally intensive. And so we're looking for sort of shortcuts of how you can image on the faster timescales much more rapidly. And this leads me to, so the interesting thing about Yuanming's results that I don't have on this slide here, looks like I may have uploaded a slightly old version of my talk, is that all of these 6 variables she found in the ASKAP field happened to be aligned in a very straight line on the sky, and showed that there must be a single screen in front of these background sources that was causing the scintillation, which was an interesting result that is only possible for the first time because of the ASKAP field of view. Now, what we're excited about in phase 2, and in relation to what we would need from Pawsey, is that we want to be able to do this routinely on all 10 and 12-hour observations that we have access to. So we want to do this really fast imaging. As soon as the observation is done, look for high time-scale variability, extremely variable sources, and then hopefully, if they're of interest, do follow up straight away with other instruments. And this is something that there isn't the capability to do so far. I mean, we're just developing the software to do the fast imaging efficiently, and then the transient detection efficiently. And so in terms of our supercomputing requirements that would be different from our standard survey, we would want to have dedicated processing that could do this, because obviously it would defeat the purpose of doing this very rapidly if we then had to wait in the queue for a long time to actually do the processing. So this is the thing I'm most excited about trying out in the phase 2 pilot. And I think it's something that also we'd be very keen to talk to Pawsey about how we would actually do that on the system, because it does have different challenges. I assume that might be the bell. I didn't hear a bell, but Annie's appeared.
That's right. Yeah, I did the bell, trying to be very quiet about it, but yeah, then all of a sudden I appear. That's okay.
Okay.
All right. Thank you.
That's me done. Yeah.
Thanks, Tara. All right. Next up, we have Mawson.
Hello, everybody. All right. So yes, I'm a PhD student with the craft team, and yeah, we're on the hunt for a fast radio burst. So I think one of the more exciting parts of that science in the next couple of years is going to be see what else that we can do with fast radio bursts to constrain the kind of environments that they propagate through. So ASKAP provides us with some of the best quality data in the world to do this kind of science with. And a couple of examples of this are shown here in these 2 plots. The right plot is a dedispersed time profile of a fast radio burst, and we can see that we can make out quite a bit of temporal structure there. And this is some 4 orders of magnitude above our lowest temporal resolution that we can go to. So we really hope to be able to make out quite a few different propagation mechanisms that haven't been investigated before, and use fast radio bursts to kind of constrain the environments that they propagate through in this sense. Similarly, we can provide some of the best localizations in the world. Sorry, go back one. By using the interferometry capabilities of ASKAP to localize these bursts on the galaxy. And so by doing this, we kind of get an idea of what environments they travel through. All right, so move over to the next slide. Just as I said before, I'm interested in what else we can constrain environment-wise, because FRBs have already been shown to be awesome probes of the intergalactic medium. This is shown no better than in this plot here by the late and great J.P. McQuarrie, who found the missing baryons distributed through the intergalactic medium by constraining the contribution from the IGM to the dispersion measures of the bursts, which gives you kind of a sense of how many electrons are along the line of sight. So if we move forward another slide, another interesting aspect that came out at a similar time was that we can also use these bursts to probe foreground kind of mediums. So this burst was discovered in 2018, and as we can see, this top right plot shows how it was localized to a background galaxy. But in the foreground, we see that we also have this galactic object that it passed through at about 20 kiloparsecs. So it passed quite deep within the galactic halo of that foreground object. And so we got a kind of sense of the medium that it might pass through. In the case of baryonic matter, it managed to constrain the fact that the gas was quite low density and had a low magnetization, wasn't very turbulent compared to what some models might have expected. So that was rather interesting. And on the aspect of what I'm most invested in kind of this science is constraining the dark matter properties. So if we move over to the next slide again, as these objects pass through foreground halos and whatnot, they become influenced gravitationally by the dark matter that's there as well as the baryonic matter. Now this left-hand plot here is a source plane simulation that shows how the magnification of that FRB will change with position. So this is set up and depends upon the kind of power spectrum of your dark matter distribution in the foreground galaxy. And similarly to its magnification, its time delay will also be affected. So by constraining the time delay that we see on our fast radio bursts that pass through any of these foreground galaxies, we can then inadvertently constrain the power spectrum of that dark matter distribution. And that might be able to lead us to say something fundamental about, you know, properties from the free stream potential candidate particle mass for dark matter in that halo. And all we need is to observe some more bursts that pass through those foreground galaxies in a way that is close enough to provide us with an interesting result. And so those are definitely the things that at least I'm most excited about. And I can say for the rest of the collaboration that they're similarly excited about the kind of baryonic physics that we might be able to constrain and the environments that we can kind of give the properties of as these fast radio bursts pass through. Thank you very much.
Thank you, Mawson. Thanks very much. I'm not having to use my bell. I'm feeling a bit left out here. Anyway, you're all sticking to the 5 minutes. Great. Chandra, can you please turn your camera and microphone on and join us on the stage?
Yeah. So hi, everybody. I'm Chandra. I'm a recently appointed postdoc here at CSIRO Kensington. And so today I'm going to be representing the WALLABY survey on behalf of the WALLABY team and telling you why I'm excited about the WALLABY survey. So if you go next. Yeah, so first things first, WALLABY stands for the Wide Field ASKAP L-Band Legacy All-Sky Blind Survey. So as you can clearly see, someone's put in a lot of effort to build or construct that acronym based on a native Australian animal. And so for that reason alone, I think you should just go and vote WALLABY as having the best acronym among the radio surveys. So go and do that in the break. So that aside, WALLABY is essentially, is essentially going to observe the entire southern sky and hoping to detect the H1 21 centimeter emission from the neutral atomic hydrogen gas in these galaxies. And the H1 gas is important because it's the primary reservoir from which stars are eventually formed in galaxies. And WALLABY is essentially going to detect about 200,000 sources in H1, and which is a phenomenal number. So what are some of the main goals of the WALLABY survey? So some of the science goals include trying to understand galaxy formation and evolution on the basis of trying to study how the H1 gas evolves into stars and forms stars eventually and things like that. as well as also trying to understand merger rates and things like that based on the H1 observations. And finally, WALLABY, because of the fact that it can deliver accurate redshifts for hundreds of thousands of galaxies, we can also constrain our cosmological parameters in the local universe pretty nicely. So WALLABY is essentially going to be a game changer for our understanding of galaxy evolution. So what's the current status quo of the survey? So essentially, all of the early science and pre-pilot observations and processing are complete, and in fact, a number of papers have already been published based on those results. And we've also completed the processing of the phase 1 pilot fields that encompassed of 3 pilot fields, and one of them is actually shown here to the left, which is basically the WALLABY H1 map of the Norma cluster. And as you can see, it's each of those bright points that you see in that image is essentially a galaxy by itself. And so it shows the amazing potential of WALLABY to cover large portions of the sky in a nominal amount of time. So currently we are headed, we have actually started the phase 2 pilot surveys, and we have gathered all the observations and essentially waiting for the data to be processed. So if you go next. Here's another example. Here's another stunning image of one of the pilot fields, pilot 1 fields from the WALLABY survey. And this is essentially the Hydra cluster galaxy. And again, each one of those bright points that you see is an individual galaxy which has some H1 gas detected in it. So that really stunning images already being produced by WALLABY. So if you go next. So finally, this is my last slide. So I'll just quickly go through what really excites me about the survey. And essentially, it's, we're going to be detecting hundreds of thousands of galaxies, and which means that we can do all kinds of really cool things. So one of the things that I'm really interested in is trying to understand the gas kinematics of galaxies, as is shown by those velocity maps to the right. All galaxies come in different, the gas kinematics of galaxies vary, and this variation may be because of, can tell us something about, if they've accreted gas from their surroundings or if they've interacted and things like that, and that will enable us to sort of get a better idea about how they evolve. So this is something that I'm interested in, and then one of the things that I'm really interested in doing is to use machine learning techniques to classify these kind of kinematic features. That's one of the things that I'm really interested in. And also, I'm very keen on trying to understand, the effects of some intrinsic properties like mass and angular momentum on the H1 gas fractions of galaxies, and how they sort of have an effect on their evolution as well. And finally, I'm also interested in the direct detection of H1 at the very edge of the WALLABY survey redshift at about Z0.23 using machine learning techniques. Again, this is essentially led by Ivy Wong here at CSRO and her team. So that's probably it. And these are the things that essentially excite me, and I'm happy to take questions later on. Thank you.
Thanks, Chandra. Perfect timing. All right, next we have coming up is Nick. So Nick, if you could turn your camera on, perfect. Over to you.
Great, thank you. So today I'm going to talk about GASKAP, and this stands for the Galactic ASKAP Survey. This survey seeks to create truly unprecedented data sets of the H1 and OH in both the Milky Way and Magellanic System. The order of magnitude increase that we'll get in sensitivity compared to previous surveys, combined with the unparalleled angular and spectral resolution that we'll have, makes these systems really the perfect laboratories to study gas dynamics. So for example, feedback processes, accretion onto our own galaxy, and the interaction between the large and small Magellanic Clouds in the Milky Way. We are also looking to measure H1 in both emission and absorption. We're going to do that in conjunction in order to study phase changes within the interstellar medium. And something that I'm quite keen on, I'll talk a little bit about, is use these unprecedented spatial and velocity resolutions to study the relationships between velocity and density features. So this can help us characterize energy injection into the turbulent medium, which then we can relate back to models of star formation. So today I'm going to focus on the H1 component, and then Chenoa after me will provide background in regards to the OH. So we use a very unique way of imaging our data. So typical full field ASKAP images are produced by creating deconvolved images of each beam separately, and then you stitch them together. So this works for all other surveys where the emission is very small scale. So for example, you have a distant galaxy that's quite small in the sky, and this is contained within a single beam. So this does not work for our targeted H1 emission, so it's demonstrated by this figure here, where we have emission that extends over the boundaries of many different beams in a single image. So we utilize an imaging method called joint deconvolution. This is where we take a single large image and we grid all the measured visibilities onto this single grid of all the formed beams, and before we move on to the deconvolution. So this is necessary in order to recover the largest scale of emission. So however, this is, of course, and this is the theme today, it seems, this is immensely computationally expensive. So what I've done is wrote a custom pipeline that utilizes CASA. This is a third-party software suite. But we're currently working with the software group at CAS with the hope that we can utilize upgrades to Pawsey's facilities and for the ASKAP soft processing suite so that we can run our joint deconvolution imaging in a much more efficient manner. So this is something that probably I'm most excited about in the upcoming year, because this will provide much more time for me to do actual science. So if you can do the next slide, please. Great, thanks. So we have tons and tons of great images to do science with. So some of the work I've done is use statistical tools to characterize density fluctuations in the H1 emission that's caused by turbulence. And for the first time, we're seeing that the turbulent properties of H1 are actually quite similar to what we see in the cold molecular gas, such as CO. So this is particularly interesting because the typical notion is that H1 is rather trans or subsonic, as opposed to the supersonic environments that's seen in the molecular gas. So other working groups, such as Susan Clark's filament group, have characterized the orientations of H1 fibers, and they're relating this back to polarized starlight to obtain estimates for the magnetic fields. And most of us saw on Tuesday at the Science Forum that James Dempsey's absorption pipeline is going to give us a really novel view into the cold H1 gas that exists within the Milky Way. If you come to our whiteboard at our table during the discussion section, you'll be able to take a look at a lot of these cool images that have just incredible features in them. So we're really excited to see what science is going to come out of our phase 1 data. And we are looking to really create the gold standard for the Milky Way and H1 observations for the Magellanic System. And yeah, we're looking forward to processing our phase 1 data and then moving on to phase 2 and trying out the upgrades to ASKAP soft and get our joint deconvolutions ready. So thank you.
Thank you, Nick. All right, Chenoa, can we have you on stage, please?
Hi, for those of you who don't know me, my name is Chenoa Tremblay. I'm a postdoc with CSIRO Astronomy and Space Science, and I'm the project scientist for the GASKAP-OH side. So similar to what Nick has already said, GASKAP stands for the Galactic Australian Square Kilometre Array Pathfinder Survey. Maybe not the most creative of all of the survey team acronyms, but it aims to study the evolution of the Milky Way and the Magellanic Clouds through their interstellar gas and the star formation. As such, the survey is designed to observe both the small and large Magellanic Clouds and the galactic plane through the H1, like Nick had just mentioned, and the 4 hyperfine transitions of hydroxyl at 1.6 gigahertz. And I'll be focusing on the OH. Next slide. So OH, or the hydroxyl radical, is the first molecule discovered by a radio telescope. And the molecule still provides information about the largest variety of astronomical sources displaying maser activity, which is the super bright bursts that molecules can give off, and it observed in both the galactic and extragalactic sources. Molecules such as OH are important tools for understanding the age, physical, and chemical conditions of the environments in which they're found. For example, stars form when clouds of interstellar molecular gas cool and collapse under their own gravity. Observing this molecular gas is really important for understanding how stars are actually born, how they interact with their environments during this process, and understanding what leads to the conditions that are conducive to star formation in the first place. We can get all of this with just OH. Even better, we can simultaneously observe the clouds where new stars are forming, where huge red giants of aged stars are puffing off their atmospheres into space, and explosive shocks of supernova or the stellar deaths. Next slide. So GASKAP is going to be the GASKAP-OH survey is going to be the largest, most sensitive survey of all times, with all 4 lines around the 1.6 gigahertz. And it is the most complete sample ever. That's incredibly important because otherwise you can be biased with what you're looking for. If you want to get the statistics of how sources are distributed, what other things they might be associated with, and how their properties connect to their environment and what that says about the big questions about star formation and stellar death, then we need these types of surveys. And for our survey, we have a velocity resolution of 0.1 kilometers per second within our own galaxy, and that allows us for studying of really detailed motions within the emitting gas. We also have a spatial resolution of about 6 arc seconds at these frequencies, so we can place very precisely where these objects are sitting. Now, neither of these by themselves are revolutionary, but when we combine this with the field of view that ASKAP gives us, and therefore the survey speed, there's not another telescope that can match it. And this makes it much easier to find sources quickly and to extend the regions that we may not have thought to look if we had to be more precise within our locations. Example, outside of the galactic plane. If we have we have had a number of challenges with phase 1 and some of the test data. Some of this was telescope related with the really high spectral resolution that we're getting, but also computationally as well. The cost of the ability to be able to study these in high resolution for the motions as well as their positions makes for very large data sets per every footprint that we observe with ASKAP. And this means that opening and inspecting the data is challenging, source finding, and creating some of the spectra, which some of the other teams have seen as well. And some of this can be handled with some of the processes, including the combination of Pawsey with COSDA as well to break up some of the data to make it a little bit easier. But eventually we would like to also be able to do some of the stuff that the GASKAP-H1 is doing, where not only look for little bits of light in point sources, but also look at the diffuse distribution of OH towards sources in the galaxy as well. So I'm looking forward to what the survey can really offer as far from scientific capabilities. And I'm looking forward to discussing any of this at the table discussions later. Thank you.
Thank you, Chenoa. Great summary. All right, next we have up is Richard.
Okay, I think I've got the microphone now. I hope you can hear me clearly.
Yes.
Great. So I'm presenting this on behalf of Jonghwan Rhee, who's not available, and of course and he was presenting on behalf of the entire DINGO team. So I can only speak confidently to some fraction of his slides, but I'll do my best. So next slide shows our science case. So this is what happens when you cast from Keynote to PowerPoint. The PI is Martin, who's in the audience, and what we're trying to do that is different from the previous H1 surveys is to go significantly deeper. The WALLABY survey is wide but shallow, and that will be exploring the local universe, but DINGO is looking at a smaller area of the sky, going much deeper and hoping to push out to redshifts of about 0.43. The science goal of that, of course, is because the theory of there's a significant gap between the theoretical calculations for the cosmic H1 density and the observations, and DINGO will be able to address this region between 0.1 and 0.4, which is where, certainly in radio, that deviation is most profound, most clear. So the outcomes of this investigation will be addressing the mass assembly and the impact environment by selecting the galaxies into clusters or non-clusters, red, blue, etc., and checking the fundamental scaling relationships such as the Tully-Fisher relationship, size-mass relationships, etc., etc. Okay, next slide. As I said, the this survey is targeted to a limited number of regions in the sky, which we will observe for thousands of hours. Well, 5 times 500 hours for the DINGO fields, DINGO deep fields, and then there's some ultra deep fields which are 5 times longer observations. And these two surveys will be probing the galactic structure, as I said, out to a redshift of 0.4. So next slide, please. The method is pretty well known. It would be stacking. There would be very few direct detections with the ASKAP sensitivity at these high redshifts. But the pilot survey has already shown that we can use the gamma locations for the known galaxies to stack spectra. And already, even from the pilot ASKAP-12 data, there's some very, very clear detections coming back here. And this is stuff from Jonghwan's work, where he's stacked all the galaxy expectations to produce 10 sigma detections, and you can already see there's a clear distinction. But we're able to distinguish between red and blue galaxies. So this is extremely promising, and this is showing that with the DINGO will deliver on its science goals. Now, if we go to the next slide, we start to drift into where I'm more interested, which is how we can extend DINGO. I think Jonghwan has already shown that DINGO will produce exactly what is promised, but how can we go further? DINGO's greatest challenge is the data size, and so we are looking for 4 times the frequency width, so that's already 4 times the number of channels. We're looking for, as those galaxies are further away, we need let's say 4 squared times the sensitivity to get the same. But also because they're further away, and we would like to start to resolve these galaxies to separate anything that is in a cluster, we'd really like the 6-kilometer data. And for the conventional analysis, that would be about a 400 petabyte data store. We've been looking at an alternative way of storing the data on the grids, which I think is extremely positive for all the surveys that are challenged in terms of data storage, both spectral line, well, I think nearly always spectral line, but EOR and H1 storage. If we go on to the next slide, we've built a pipeline. I'll skip this in terms of time. And so we're comparing 3 pipelines at the moment. The conventional visibilities, which is, imagine that you had all the data. No, this one, yes, please. V for the conventional visibility analysis, and that produces what we consider the ground truth. We've got this gridded data stacking pipeline, which is, as you can see on the right, perfectly matching the visibilities. And then we're comparing that to the conventional stacked image analysis, where you can see that the conventional processing diverges from what we consider ground truth as from full visibility stacking. We have a Pawsey co-funded postdoc to work on this, and we're very excited about what the outcomes will be. Thank you.
Okay. Now we have Elizabeth. If you could join us on stage, that would be great.
Hi everyone, my name's Elizabeth Mahony, and I'm just going to give a brief overview of the first large absorption line survey in H1, or the FLASH survey, which is led by PIs James Allison and Elaine Sadler. I think a few of my slides may have been accidentally cut out, but that's okay because you can see some very exciting detections here, which is the main point. But I just provide a little bit of background of why we want to FLASH survey first. And our key science aim is to understand how galaxies have changed over the last 10 billion years or so. So we know from our previous studies of galaxy evolution that galaxies look very different at intermediate redshifts of about 1 or 2, so 8 or 10 billion years ago, compared to what they look like today. So at intermediate redshifts, they're much bluer and they're forming lots of young, hot blue stars and actively forming lots of new stars at a very high rate. Whereas local galaxies are much redder and have a much older stellar population and are not forming anywhere near as many stars. And so we know the star formation rate has declined quite rapidly since these redshifts. And we think this is because of the fuel supply that goes into forming stars, and that's the cold gas. But our observations of cold gas, particularly at these redshifts between about 0.5 and 1, where the star formation rate really drops out, is very poorly constrained. Oh, hello. Yes, okay. Yeah, so this is just an illustration of what galaxies look like at redshift 1 to 2, so about 10 billion years ago. You can see they're much bluer, actively forming new stars, and then in the local universe at redshift 0, they're much redder and have an older stellar population. So on the next slide, you can see on the left, you see how the star formation rate declines. It peaks at about 10 gigayears, or redshift 2, and declines very rapidly towards the present day. And on the right, you can see a measurement of the cold gas content of galaxies. And so for the FLASH survey, we're really interested in probing the cold gas content of galaxies at redshifts between 0.4 and 1. And you can see this is where it's really unconstrained in this plot. So on the next slide, you can see it turns out ASKAP is a really ideal telescope that's perfectly suited for this kind of survey, so a large survey in H1 absorption. And there's a few reasons for that. First of all, ASKAP has a very large field of view, so that means we can survey the whole sky quite quickly. It's on a very radio quiet site, which is important, means that we're not too badly impacted by RFI. And it opens up that frequency range of 700 megahertz to 1 gigahertz, which when we're looking for the H1 line, that corresponds to redshifts of about 0.4 to 1 in redshift. So really probing this key intermediate redshift range that we're interested in. And the third advantage of ASKAP is that it's very wide bandwidth. So at 300 megahertz of bandwidth or a bit less, in one single observation, we can cover that whole redshift range at once. So for FLASH, we'll be carrying out an all-sky survey in H1 absorption. And it really only takes us a few months of total observing time to survey the whole southern sky. And we'll be looking for H1 absorption signatures towards bright background radio sources. And the advantage of doing that, as opposed to looking for H1 in emission, like the WALLABY or the DINGO surveys, as we've just heard about, is that it allows us to go out to higher redshift. So on the next slide, you can see this is some of the data that we're getting from our pilot survey. So we take observations and Matt very kindly processes all our data for us. And then we get a continuum image that looks similar to this. So you see the full ASKAP field of view, 30 square degrees. And from that image, we identify the bright sources that we want to look for spectrum and search for H1 absorption towards, which you can see in these circled points here. So the other point that I wanted to make is that FLASH also will provide kind of a mid-tier continuum survey of the southern sky as well. And on the next slide, you can see one of our detections. So this is the science that we're really interested in. So we select all those bright sources, and then we look at the spectrum and search for H1 absorption over that entire frequency range. So you can see here the nice clean spectrum we get from ASKAP, and we're looking for absorption signatures that look like something like this here. So this particular object is a galaxy at redshift 0.5 that's associated with this reddish, blobbish looking galaxy you can see on the right there. So on my very last slide, because I can see Anne has just appeared. Well, that's okay. But very last point that I wanted to make was that Pawsey and the collaboration with Pawsey is really critical for the FLASH survey, because our data rates are enormous, as has been a common theme for all of the ASKAP surveys. And it's really because we have such a large field of view and we want all of that wide bandwidth.
And our lucky last, we have a Pawsey presenter. We have got Mark Rhee. Mark, if you could join us on stage.
Hi, my name is Mark Rhee. I'm the head of scientific platforms at Pawsey Super. I'm going to talk fast to a very complicated. I'm really going to talk about two things in my 5 minutes, or maybe 4.5 since I lost some time. What are we doing, and when are we doing it? There's been a lot of pretty keen interest expressed in the previous presentations around the infrastructure that Pawsey's building. In a nutshell, this is the infrastructure that we're building. So everybody has probably heard about Photonics, the new supercomputer that will become available over the next 12 months. It is one part of, and a large part of our technology deployment, but not the only part. So we are also, we deployed our new cloud infrastructure at in the early part of last year. Over the last 12 months, we've deployed the ASKAP ingest cluster and the MWA cluster Garawala, and we're still running the Topaz GPU cluster. In the meantime, we're also building new network interfaces. So as we're building the Photonics, our new supercomputer, we're deploying a new backend network. And so what we're going to have at the beginning of 2022 is a very large supercomputer, our cloud infrastructure. All of the infrastructure should be running on at least 100 gigabit per second interconnect, and we'll have a backbone of 400 gigabit per second that will talk to an external 100 gigabit per second external firewall. Internally, the two largest infrastructures that we're building are, of course, the supercomputer and our new storage system. The new storage system is moving to an object-based infrastructure, and a very large proportion of it, about 60 petabytes usable, will be pure disk systems deployed with Ceph. Next slide. So when are we doing all this? So the answer is we're doing it right now. The actual supercomputer, which is the biggest part of our infrastructure, is a multi-stage deployment. I put stage 1 and stage 2 here. It's actually a 3 or maybe 3.5 stage deployment. An initial stage, which is our test and development system, will hopefully, if everything goes according to schedule, arrive in the center next month, actually, and that's going to give us some of the first hands-on testing with this infrastructure. Phase 1 is currently scheduled for Q3. It's 2 petaflops of CPU compute, a few current generation GPUs, which will be mostly for internal use and preparing for the migration to the new infrastructure. And then at the beginning of 2022, the other 95% of the compute arrives, which is the remainder of the 217,000 CPU cores and all of the next AMD. And that'll be available in, I think, according to schedule, in the ballpark of Q1, Q2, 2022 for users. In the meantime, the rest of the infrastructure is getting deployed as well. The long-term storage deployment is underway at the moment. We received the racks a few days ago, and over the next few months, we'll be getting that ready. So I think, broadly speaking, we're looking at kind of a Q3, Q4 deployment for most of the infrastructure, with the exception of the supercomputer, which will arrive at the beginning of 2022. We're expecting 2022 full operations for all of the infrastructure, and of course we're going through a migration process for all of that infrastructure, both the storage and the supercompute, and we're making sure that all of our users and user communities have a full and, I would say relaxed, but a fulsome time to achieve a migration from the old infrastructure to the new. We've made preparations and built contingencies around the operation of the old equipment to make sure that we can really do that in a way that meets all the needs of all of our users and user communities. If you come to my table after this, I can expand about this in great and tedious detail. I think that completes my talk, and I think I'm ahead of time.
You are indeed, and I'm glad we didn't lose you into a portal black hole or something. So thank you. So we are now at the end of our lightning talks, and shout out to everyone doing what you did, providing your survey summaries and goals, and what you're, very interestingly, what you're excited about is very hard to do in 5 minutes. So applauding you all for that. Really, really interesting and well done. And now I'll invite to the stage Lachlan and Pascal, who will give a very brief wrap up.
Well, yeah, sure. So hello, everybody. I hope, one, that this has been useful. I think it's been, from a policy perspective and asking some quite technical questions from some of the groups, it's been useful for me as well to try to make sure I understand how everybody's doing and where everybody stands and what challenges they might face. We're going to try to present a quick summary of what we think could be really interesting, and maybe some of the challenges that we should try to think about as we're going forward, because of course we have a new system coming up. We've managed to have a new cluster going up with ASKAP ingest, but then going forward, Photonics will have a real drastic change in sort of its compute, because it'll go from CPU to GPU. So it's something to think about for everybody out there. And of course, there'll be a change in how you access large data. I know this is if everybody in ASKAP could get their wish, they'd have an infinite hard drive that they could easily access in size, right? Because I know data volumes are a challenge for essentially everybody in ASKAP. I'll start summarizing, but Lachlan, do you have anything else you want to add?
No, look, I mean, I came up with this concept as an opportunity to get people together. I mean, ASKAP's such a big team. Pawsey, it's very easy for there to be no connection, no communication between all the people. And apart from that, you know, it was really interesting hearing all this stuff. I don't have anything kind of particularly enlightening to say, but I did have one thing, and that was Richard gave the best COVID reason, I think, or the COVID statement, which was that he hasn't had his hair cut because he only gets his hair cut by an Indian gentleman who works near the airport in Dubai. And since he can't go to Dubai anymore, he just doesn't get his hair cut, which I think was fantastic. So, and we'd miss out on those sorts of things if we didn't have this kind of event. No, I think hopefully we'll be able to recreate this and make it a more regular thing, and keep everybody in touch.
Yeah, so I was going to say that for the Pawsey side, it's been interesting because most of our communication is particularly with ASKAP operations. There's a lot of communication there, right? Because we obviously are helping them run the ingest cluster, try to get them off the ground. And so there's a lot of interaction that way, and sort of the challenges we know about are challenges usually through ASKAP operations, people raising tickets and so on. But of course, everybody has processing that they all do, and they all are trying to face these challenges. And so it's been kind of, as I said, pretty interesting to see the scientific goals of everybody, the overlap. So hopefully the networking has been useful for everybody, that you got a chance to kind of chat with people that you hadn't chatted with. I got a chance to chat with people from Craft that I hadn't really had a chance to, because it's a pretty new survey. But it's something I want to mention is that normally I get the impression that the standard challenge that everybody's facing is the data volume. And that is true, but I would like to make sure that you can chat to us. Make sure you feel free to kind of contact Pawsey if you're running stuff on Pawsey. There are a couple of update projects and Pacer projects. As Richard mentioned, they have a Pacer project, which is meant to embed someone between Pawsey and their survey to kind of make sure it can go somewhere, right? Because one of the biggest hurdles, you want to do science, the computing challenges are there are hurdles to overcome, and then you can do really new science. You can keep moving forward. So I was going to say that for everybody out there, please, feel free to start contacting us. We have a couple of update projects and Pacer projects that are ASKAP related. But if you have something like, this is actually a challenge we're facing, and we want to run it on Pawsey systems, but it's a kind of a unique challenge, it's possible that we'll be able to help you going forward, because the computational landscape will change quite a bit from CPU to GPU, and you really want to, try to make sure you can get your science done as fast as possible using the least amount of resources, so that you use the least amount of electricity, and you try to be green too. I think it's kind of important that we all try to aim for green compute. So optimized, fast codes that do everything you want in the smallest amount of time. And that would be a really good thing for everybody. Anne's back.
She's ringing her bell.
Exactly.
Yeah, I assume that was the case.
If Anne shows up, it means party's over. All right. So again, thank you, Pascal and Lachlan, for the wrap up. And please do reach out to us, as both Pascal and Lachlan are saying. Thanks all, and we'll see you next time.
Thanks, everybody. Thanks for turning up.